So I'm going to go over an introduction to the resistivity tools, which will be quick and a little bit repetitive, but then I will go into an old example that we've always used for thin beds resistivity analysis, and this will show what Joaquin was talking about this morning on how in some cases the actual, or what you want to use for the Earth model resistivity, will be very different from what you see in the logs, and then we'll work on that manually, and then Joaquin will come back and show you how you do it using the modern automatic inversion approach with MCMC. All right, so this is basically what he showed you this morning, and this is what we're going to see in this thin bed example. And somebody say something? Okay. Where in the first one you see what we call the conventional interpretation, where you just assume that the log is correct. But then since we have simulators in UTEP wells, you can simulate it, and you realize that on this thin layer, it's not actually going to reach the full resistivity that it should. And so in order to get the simulator to match the actual log, you have to increase the resistivity in that layer, or decrease if you have the opposite difference. And then in the end, when they match, you can assume that your Earth model is a more realistic value of resistivity, and that then you can use that for your formation evaluation. And so we have over 40 sims, including variants available in UTEP wells, and here's a table of them basically, and this shows you the types of tools that we have available, as well as the different variants of each tool, and then what they're able to do in terms of whether they handle anisotropy, whether they take additional parameters in addition to resistivity. Some of them will take electric permeability or magnetic permeability, and then also whether or not they will take into account dipping beds or angled wells. Unfortunately, it doesn't say how fast any of these are, so you have to find that out yourself. Okay, so you see we have quite a mix of 1D and 2D, and then you see throughout a bunch of the semi-analytical assay versions that Joaquin mentioned, which are nice first choice for running your resistivity because they're fast and accurate. All right, and then so just to review what we mean when we talk about 1D versus 2D resistivity. In 1D, we assume that all the resistivity and permeability and stuff changes along the borehole, but it has no invasion. So whatever you see at one point in the borehole, that will extend basically infinitely into the formation. And the only way that will change is if you see, like in the picture here, due to angled beds, technically at some point you're going to, if you have angled beds, you're going to hit variation in another, from another bed. And that is if you went out exactly perpendicular. But in actuality, I think most, if not all, of the 1D sims take into account the angling of the bed, and so they'll just calculate, even if you have really high angles, where that tool will see the nearby beds because the angle will bring them in range. And so in most of them, I think, it also assumes that, I mean, a lot of them will only give you one angle. And so in that case, you don't really see this effect, but we end up breaking up the sim into separate sections that all have a fixed angle bed. And so it's sort of an approximation. So that's one of the approximations that's made in the 1D, so first approximation is probably that the resistivity doesn't change as you go out from the borehole. And the second approximation is that nearby beds are parallel to each other. And I think some of the simulations maybe can handle continuously varying beds, but a lot of them I know that we break up like this, as shown in the picture. And then the difference between this and the 2D is that the 2D, you can have invasion zones, and so then you can have varying number of values of resistivity as you go out cylindrically from the borehole. I don't think yet we have any actual complete 3D sims, although I think they're working on some. But we do have the 2D ones, and now the 2D ones, of course, have the limitation that they generally assume that the bedding is perpendicular to the borehole. So you can see these kind of take up two different cases, and each have their own approximations and handle different types of calculations. And all of them sort of assume azimuthal symmetry, at least in the layers. And again, the only things that, as far as I know, that they take into account are resistivity, permeativity, and permeability. And I don't think any other, other than the geometry, I don't think any other values are taken into account. Okay, so what we're going to do then is we're going to run through an example that we always use to show this. And it's our thin bed example, and you have it involves just creating a new well, and there's actually a let's see, we have I guess this is in Monday now. Yeah, so there's a PDF that kind of describes what we're going to do, but it's pretty simple. So so you probably don't really need to even look at it. We're basically just going to load the thin bed resistivity last file, and then we're going to plot a couple of tracks that we see here, and then plot some logs, and then we're going to try to match the simulated log to the loaded resistivity log, and then see what effect that has on the Earth model values. So I'm just going to do this. So we start with I'll start with a new well. And then the first thing we're going to do is import the log file. So we'll get this from the workshop materials. In my case, I downloaded the folder. Probably you did too. So it's on my desktop. And then in workshop materials, we have this thin beds resistivity less. And so you can load that, just like Joaquin showed you this morning. And now you can see over here that we have the last file loaded in the well under log sets, and you can see all of the logs that we have available there. And so in particular, you can see that we have a gamma ray log, and we have a bunch of resistivity logs here. And typically for this example, we use the RT90. And so that's the one that we're going to use to plot today. So again, as he showed you, if you want to get from here to the well, you can just ask for the well interpreter and it'll bring that back up. Likewise, if you have a bunch of wells open and you want to get back to the main window to look at your wells or your log sets or something, you can always come down here and say show main window. So you can get back and forth between these very easily. So now we're going to plot the gamma ray and the resistivity. So first, in the first track, we're going to get the gamma. Oops, we want to do the log set. So we get the thin beds log set, and then we'll plot the gamma ray. And it comes up with a reasonable range to start off with. And so then to make another track, we can just hit the plus up here. And in the second track, or in this case, it's the third track, technically, we're going to plot the thin beds RT90. So go to RT90, and then because this is a resistivity, we want to make this logarithmic. And we'll put it down a little bit lower. Okay, so get it so that way it shows up well in the middle of your track. And if we wanted to, we could also put the boundaries on there. It depends if you want to see them or not. We can see if we need them later. Oh, we don't have them yet. So, all right, so we'll start off with that. And now, in order to do this, we need to have some boundaries so we can have some Earth model resistivity values to vary. So what we're going to do is use the gamma ray is typically what we use for boundaries. You could do the resistivity since that's what we're going to be changing, but in this case, I'll stick with the gamma ray. And so you can put the gamma ray over here and move the well over so you can see what happens when we. So I'm just using the default values for the populate boundaries or detect boundaries. So it's set gamma ray, and usually we should probably make this even the default that this is unchecked, because a lot of times if people want to, if they don't like what they get the first time, they want to redo it, not add more boundaries. So keep in mind that if you want to do this more than once, you should generally want to probably uncheck the keep existing boundaries. It's hard to imagine many cases where you'd actually want to keep the existing boundaries. All right, so now if we hit this, you can see that this immediately populated what looks like some pretty good boundaries for the gamma ray. And if you want to see, well, actually, I don't know if he showed you this, but if you want to see how well they match up for the resistivity, you can hit your control and then drag your boundaries over, and you get a copy of them in the next track.
And you can do it with. Sorry, I was just going to say you can do it with control or right clicking. Sorry for interrupting.
All right. Oh, okay. Yeah. So if I wanted to see this over here, which probably wouldn't make much sense. Yeah, so now I'm right clicking and you get the same thing. So, and you can also delete this one. Delete CTR. All right. And so if you look at this closely, you can see that maybe it doesn't match everywhere. The ideal positions for that you might want for the resistivity because it matched it up as well as it could for the gamma ray. But we can leave it like that and see how well it works. But you can, things like this one, I'd probably want to move up really a little bit or something. But now you also need to check that you have, before we do the simulations, you want to be sure that you have your modeling interval where you want it. And so in this case, I'm going to put it so we're just modeling the area where we have the log. And you can also set that over here if you want to put specific values, or if you just want to. And then now the next thing we want to do is, so we can find a starting position. And again, this will be what we call the conventional population of boundaries or choice of values. And so if we go to the populate properties, you see that resistivity is one of the default properties here, and we can select the RT90 as the log to populate that from. And then populate properties. And there was a little progress window that popped up in my other screen. And now if we plot the Earth model, which is a thing that we really want to update, and we go down to the resistivity, you can see that this is what we called before the conventional choice of values. So it just picks because this is a simple log, it easily finds the peaks of each layer, except for the lower one. Okay, so now the other thing that we can do is we're going to want to compare the simulation to the log, and then change the Earth model until they match. And so you can either try to plot the simulation first, or you can run the simulation then plot it. I'm not sure if this will work, so I'm gonna try to pick a deep resistivity simulated log. And we see that RT90 is listed under the deep resistivity. So ideally, this should bring up, when we run the simulation, it should bring up the logs, and we'll see what happens. All right, so now the resistivity, if you're going to run this manually, you just pick the resistivity symbol icon up here, and then you get your resistivity window here. And as we mentioned earlier, you have your choice of some, well, I guess there was 40 total variants, but you have probably about 20 or so different tools here. And so in this case, we're going to use the AIT. If you can't use AIT, if you're following along and you don't have Schlumberger allowed, you can use the DLL 2D mode matching. It's a UT one, and you always have it available. and has similar resolution and will give somewhat similar results. But in this case, typically we show this with AIT and AITH in particular. So, and we're going to use the 2D here, even though we don't have any, as Joaquin mentioned earlier, the 2D is sometimes faster. If you don't have any invaded zones, it doesn't have to worry about any angled beds or anything, so it can be a little bit faster. So we're going to pick that. We can leave the permittivity selected, even though we haven't changed anything. So it's possible that we might actually not want to have that selected because we have some default value there. We don't know what it is. But by default, it's selected, so I'm going to leave it. Then down here, so you can, if you want, you can change the output log set. And this is useful if you want to run multiple, say you want to try one with permittivity and one without. You can run one with the default log set name, and then the other one you can put, without permittivity as at the end of it or something. And so then that way you can plot next to each other the two different things that you tried, or you can try, a different AIT model or something like that. And so I think we don't emphasize this a lot, but it's really useful in many cases to be able to compare logs with different values. So now, and also you have the option of either having the command window closed or not. And usually you'll see it run and then it'll close, and that's fine unless you have some error and you're trying to figure it out. You might want to leave it open, but we'll let it close in this case. And so now we can run the simulation, and unfortunately it came up in the other window, so we didn't get to see it. Let me try to see if I can move it over fast enough. Not fast enough to move it over.
And be careful, because if you click in the wrong place, you may make it crash. So it's okay if they don't see it. They will see it if they have it in their computer.
Yeah. Okay. I mean, the other option is I could unclick this and then it will stay open. There, it stayed open. Okay. Anyway, that's what you should see in your computer. And then it should go away if you have this closed. All right. So now we can see that this actually worked here. So we had used a mnemonic for this, and even though it didn't exist when it was created, it actually ended up plotting it. The only thing we didn't have was the ability to change this to dashed or dotted, which we usually do for simulated logs. All right, now the other thing, so what we're going to try to do is to modify the Earth model so that the simulation matches the actual log, and that's the whole goal of probably most of UTEP wells. I mean, at least the first thing that you do is to try to get an accurate Earth model based on the log versus the simulations. And so one thing that'll make this easier for us, since we're going to be doing this manually, and it's also handy even if you just want to see how the MCMC does, is to look at the difference shading. And so if we compare the RT90, yeah, pick the right ones. Fortunately, we need to come up with a way to give different names for these things. I think we actually can't change the name, but it would change back when we rerun it, so it doesn't help a lot. So I don't see this very well. I'm going to try.
I think you just need to check the check button in the other color, because it colors two different colors when the left curve and the right curve. And you probably selected the same. No, it seems okay.
Yeah, I think the yellow was hard for me to see on this screen. I don't know if you guys could see it, but I had the light yellow. It was a little hard, so I picked the orange instead. So I think it probably shows up better now. But you can see the green and the orange show you whether you're less than or greater than. And so, you know, what we see is that for the most part, the simulation is kind of muted or not reaching the actual peaks of the log. And so what that is telling us is that we need to adjust the Earth model. So, and also what you get here, let's move this boundary down. Notice that when you do this shading, it gives you an RMSD showing in this window here, and so it quickly shows you how far off your two curves are, and you have a choice of either just showing the right to left RMS or the left right. You have your choice of which RMSD you want to show, the green or the orange or both of them. And so we'll do both of them. And so our initial point here is 16.5, and then what we want to see is how low can we get the RMSD by moving these resistivity values in each of the beds, and this is the way for quite a few years that we were teaching this, is that you'd manually move these things, and it was sort of a tedious task. And then a few years ago, we finally got the MCMC in here to do this automatically for you. So I'm going to show this, not try to make too much of an effort at it, but just show you how you can do this manually. And it's useful to do it manually at least once to get an idea of what you're actually trying to do, and what the MCMC is actually doing. And so I'm going through here, and wherever it's green, I'm moving it to the left a little, and where I see some orange shading, I'm moving it to the right. And I don't really have, I mean, it's just a complete guess. I don't really have a good idea of how far is going to move which one by how much. You know, I guess if it looked big, I would move it further. But it's very dependent on how thick the layer is and what the layers next to it are doing. And so it's definitely not an easy problem to work out manually. It's just trial and error. All right, so why is this? Okay, here we go. Contrasting them basically from boundary to boundary, than what we had originally selected. And so now I'm going to run the resistivity again, see what happens. So we started out at 16.5, and after moving them, we got 14.6. So it's not a huge difference, but it's some. And so then you can see that in a lot of places the shading has become less, and so then you can just go through and see places where you see still some large amounts of shading and go and move them a little bit more. And as I said, it's not a super exciting task, which is why I'm really glad that I got the MCMC. But now we can try it again. Okay, we got 13. Actually, that wasn't very much of a change. Surprisingly, sometimes people can get this very low. Now, one thing that we do, what's interesting here, and is some of the classes we have some scripting sessions, and where we do, you can do your own, if you have MATLAB, you can do your own sensitivity analysis in scripting. And what you find, what we show in one of the classes is that if you do a sensitivity of the resistivity, when you start getting large contrast, it becomes very insensitive. Essentially, the resistivity just flattens out. And so you can make this contrast, or I could make this value probably really big from here, and there'll be very little change in the resistivity. It's kind of hard to really say how accurate these values are. I mean, obviously, if this doesn't change, if I go from 200 to 1,000, then it doesn't really mean very much. But yeah, and you can see some of these thin layers, even though I've moved them up quite a bit, they haven't really changed. So let's try this again.
Something else that might be going in some of you guys' mind is of course, the location of the boundaries, because Bruce has been playing with the location of the property, but of course, the exact location of the boundaries is going to make a difference. And you can see there's some places where it could be improved. So he can work kind of in 2 dimensions. I don't know if you want to, like,
yeah, we can try.
Yeah, in 5035, you can see that there might be some, like the boundary might not be in the best place. And this just to show you that it's a little more complex than just moving one when you have 2 dimensions and they're coupled. And it's not just, 2 dimensions, I mean the layer thickness and the layer property itself. They're coupled. And of course, there's coupling between neighboring layers because there's that shoulder bed effect. And of course, it can get a lot more complicated than just trying to do it once. And it's just basically the statement of the problem. Like we said, we don't expect you to do this by hand. I don't think anybody has the hand. Well, you'll be surprised. We do have a couple of sponsors that have shown us some highly intricate models that they've done by hand. But and of course the whole point here is that you get better assessment of resistivity, and with that you get a better assessment of water saturation, which immediately gives you a better assessment of the hydrocarbon pore volume that you're going to have in that area. So that's the point of having as accurate estimate as possible, but it's a little complicated in these cases. And we're just dealing with resistivity. Later, we're going to deal with more properties, and we're going to try to put them together, and that's going to be more complicated. But today, we're just going to work with one property at a time. Yeah.
Yeah, and as I said, so now I'm moving some of the boundaries. But as I said at the beginning, the boundaries were selected for the by the gamma ray, which didn't exactly match. And in general, I mean, a lot of times there could be a various number of reasons why the boundaries will look different for different logs. I mean, some of them they just need to be depth matched, but some of them it may be due to actual physical issues. But yeah, so I'm not getting actually too much better, I think. Actually, that got worse. I'm not sure how it got worse. Oh, because
I think that's okay.
Yeah, so,
that's
what's
fine.
That?
It's okay. We don't need to. I know that before MCMC, we had some people that could get it down to like 5 or something like that. But that, I think what you're getting it at is pretty close. That's good.
Yeah. Anyway, he'll find out when he does the MCMC how close you can get. And there it sort of takes one thing away from you, because all you have to do then is worry about where the boundaries are and let the MCMC figure out what the resistivities should be. All right. Let's see what else. If we have anything else.
That's okay.
All right. Yeah. So we'll go ahead and now Joaquin will show you the way that you're actually going to do it.
Okay. All right. So I'm gonna take over, and it's basically the same. It's the same thing. We're just going to do it with a different approach. So I've been following what Bruce is doing. So I'm just going to start sharing. And So that's where we were. And we were doing it just manually. Well, Bruce got a much better, he got much closer, but that's okay. So what we're going to do is we're going to go in here. I'm going to expand this so that it's a little easier. There's this icon that is MCMC, Markov Chain Monte Carlo. You can click on that one, or you can click Inversions, Markov Chain Monte Carlo, and it brings up the same window. And I'm just interested in resistivity at this point. So this is what the module looks like, and we're going to go in a two-step or two levels of depth explanation. So the first is we're just going to do the bare minimum to get a good check, and then I'm going to go a little further after we take a break. So first, just very simple, these are the properties that you can invert for. We have resistivity, gamma ray, bulk density. We have neutron porosity, which is indirectly the same property as migration length. We have them linked in the Earth model. You can also invert for porosity through bulk density. So the property you would get is porosity, but the one you would be modifying is bulk density. I should say the log that you would be matching is density. And then we have slowness and we have NMR porosity that were added very recently. So we'll go into some of these later. We're just going to say resistivity. And there's a couple of constraints that you can use if you know that resistivity shouldn't be less than or more than a certain value, or for other properties, this can be even more useful. You set those limits here. You can fix a property at a certain log value or core. This would make more sense with core. We're going to do it in a little bit. And it's just to make sure that the value in that layer is fixed at that value. And of course, that has some effect on the neighboring layers because there's that shoulder bed effect. And then you decide which zones to determine. Here you decide the tool. So I just need to make sure it's the same tool that Bruce was using. So it's AITH. 2D from Schlumberger. And you can see further settings here. Relative electrical permittivity is going to be considered. By default is 1, which is very good default value. And then here you have this table where you decide which log you're going to match to what simulated log. This is going to show you the logs that are simulated depending on the tool you're using. So if I say Centrify, for example, it has other set of simulated logs. But right now we're doing AIT and we 2D AITH. So it's going to be RT90 and we're going to match it to RT90, not surprisingly. We just have one. In some cases, you may want to match two. So you can do add input and we may want to match RT10, for example. And of course, we would try to match that to RT10. You can have them both. And I'm gonna do that just because it might be fun. Well, I'm gonna do it later. Let's just do RT90 and then I'll do the other. As simple as possible. And then this in miscellaneous, just auto update Earth model. Yes, whenever every iteration is going to be updated, and the simulated log 2. These are advanced, so we'll talk about them later. There's some methods also a little bit advanced. We'll talk about them later. Initial accelerated search, fine. Result diagnosis. I'm just going to say run, and then we'll see. My main window is also the other window, so you're not going to see the command window running, but it's running. You can stop it at any point. Sometimes it doesn't advance at all. That's just a bug, and it happens the first time sometimes, and it doesn't usually only happens one time when you see it. So now that I'm trying it again, it's improving. This is the misfit, and this is the RMSD. So these are two different measurements of really the same thing. The RMSD is defined here. It's the root mean squared deviation as a percentage of target values. So you just take the target and the matching log and calculate square the differences in all of them, add them, get the square root. That's root mean squared deviation. And the misfit is the same thing, but taking into account noise, which is something I'm going to do later. We're just going to assume that whatever I put in noise is fine. And you can see here, you saw that as it was running, it got better. Sometimes you are interested in getting as close of a, I'm just going to stop it now, as close of a match as possible. Sometimes you're interested also in getting uncertainty. We're going to talk about that later too. So one thing I can see here is that some of the boundaries were not correct. And because the boundaries are not correct, it doesn't matter how long I let it run, it's just never going to get there. So I can help it myself. I can modify, for example, here I can see that something like this could help. It may not. We'll see explicitly when it actually runs. Something here might have been a little too skinny. And I can just let it run and see if it does get a benefit. For sure, I can see here there's a boundary missing. That's going to be a problem. And you can see it's already 11.78, so it's better than we did before. I'm going to stop it now. And I'm going to just add a boundary here because we can see clearly there's a boundary missing. And then I'm going to let it run again. And at least from my capabilities, this is pretty much as close as it gets regarding boundary location, and at least with just the good guesstimates that I'm doing. So I'm going to say that those are the boundaries that I'm going to keep. That's it. Something I can do is I can allow YouTube wells to improve that too. So right now it's at below 8. That's already pretty close, and you barely see any difference. So this might be good enough for interpretation. But if you have very thin layers or thin layers in general, or there might be some cases where you really need a higher or better match. You may want to. There's some cases where you may want to have a better match. In those cases, something you can do is, now I'm gonna get a little bit higher here in the method. You have something called the just bed boundaries within this initial accelerated search. This bias sampling method works in a two segments fashion. First, it does an accelerated search where it tries to be as greedy as possible, trying to match the simulated log and the match log. And then it goes into another state where the matching is not going to be as fast, but the calculation of uncertainty is a lot more accurate. So I'm during the initial accelerated search, it's going to also try to adjust bed boundaries. So I'm going to allow it to run while also trying to adjust the bed boundaries and see if we can see certain modifications for those boundaries. It usually takes more than one step. Sometimes this one, it seems like it's improving slowly. So at some point we might see it. I'm not positive. This case is, the data that we're looking at here is synthetic, but it's based in a real case. By the way, it's real life inspired, but of course it's synthetic. You can see that it's clearly synthetic, and because the properties are a different dimension or a different variable, completely different variable from thickness, even though they're coupled, it tries to improve one or the other. And this one, because it's very smooth, it's going to keep improving very, very slowly. So we may not see any improvements in the boundary locations. We're probably just going to see improvements in the property, which is okay. There's going to be another case where we will see improvements in the boundaries for sure. Well, you can already see that it's pretty close to a perfect match pretty much everywhere. Any questions or comments in this section? Okay. Well, and like I was saying, that the goal is not to get the goal is to get resistivity, but it's not an isolated goal. Is to use resistivity to assess, in most cases, just water saturation. That would be the natural next step. And the way you would do that is you would go here to there's this petrophysical calculator that we're going to go into detail tomorrow, but you would go into the petrophysical calculator and you would calculate resistivity. You would use the ArcGIS and similar model to calculate resistivity water saturation from resistivities. This is what you would do. Is it possible to see differences between the initial guess and the optimized model? No, it's not something we have right now, but you can do it either with a duplicated well indirectly, or we could do it with what Bruce was saying, just by modifying the name. So let's do that. We can see how that would look like. So this, I'm just using well 1. I'm just going to rename it just so that I remember that this is the thin layers well, just to make it easier. And I can rename it. I can rename also this log. I'm going to say optimized. Well, rather than that, I'm just going to duplicate this well first. And so that this one I know it's what I meant to do first. And then in this one, I'm just going to say, rename this to optimized already. And then I'm going to forget about the one that is already with a as close as possible result. But here, I'm going to destroy what I did. I'm going to populate properties and use RT90 to populate these properties. So they're not going to be optimized anymore. And I'm going to just simulate the and I made a mistake. It's not 1D and it's not ARC. It's supposed to be AIT to the H. So I simulate. And now I get the extra. I can say LAS, well, simulated. And I have the optimized and the non-optimized. And you can see, well, I can get rid of this. That's the one that was optimized. This is the one that is not optimized. To make it more clear, I'm going to make it dotted. And you can see how different they are. Maybe I'm going to make it a little thicker so that you can really see. And the shade, I'm going to put it between they always follow the same order. So you can see how different they are. Of course, this was probably a lot of things really quick, but you get the point, and I think the question's answered. What do you think now? Good.
I think
okay.
It's good, and Inversion did a good job.
Good. Okay. Good. So now you see. Now you know how to use it. And if you have questions, of course, you can go back to the recording or send us email again. Any more questions or comments at this point? Okay, so we just used it very superficially, or not superficially, but we just went with the default values, and you saw it's very useful to do it this way. You get a good answer. You can see in RMSD the difference is 8.29 and 19. I've seen, I think 2 is the lowest that I've seen. It's not easy to get that. But if there's no questions, or if there's other question, let me know. Otherwise, let's take a 10 minutes break. We come back at the hour, so 1 p.m. US Central. And we're gonna explore a little more MCMC, play with other properties. But this is a very user-friendly tool that can be used, that we're gonna discuss a little bit more in a little bit. If there's no questions, there's a question coming. So let's see.
I'll just ask it for you. Have you played around a bit with using some of the tools to automatically adjust your bed boundaries plus or minus some increment until you have minimal change between the iterations?
Yeah,
something that ultimately you end up having automatic bed detection, because that's tends to be one of the most time consuming,
Issues, for sure.
especially is when you get something that has a lot of laminations in it.
right. Yeah, we have a couple of students working in things like that, but we don't have it right now in UTEP Wells. Yeah, for sure, that's one of the bigger issues. And the probably the main reason why you're asking that is because, well, when I'm working right now in resistivity, but if I go later to gamma ray, I'm the one thing they share is the layer location. So I'm stuck, or I'm gonna modify it, and if I modify it in gamma ray, I'm modifying resistivity indirectly. So right now, what we recommend is just use the lower uncertainty, the log that has the lowest uncertainty and lowest shoulder bed effect to invert first. So it could be density, and then assume that whatever you have in density, that's it. You're gonna use it for everything else. Of course, that it's has the issues that you point out, that maybe it's not the best location for the other ones. And yeah, we have yeah, it would be nice to make this automatically in throughout many layers, and not only detect the location of the boundaries, but also maybe do some stretch and squeeze, some what do you call it? Some QC to modify the to correct
Rubber band between the different measurements, so they have better depth adjustment. Yeah,
exactly.
depth alignment. Yeah,
depth alignment. Exactly. That's a people have done it in scripting, and they've done it in collaboration with some companies, but we don't have it's one of those projects that they did it, but it's not so easy to generalize to whatever inputs. But yeah, of course, it would be a very big improvement.